Hello students and welcome to the final lesson, Lesson 6 of Unit 3. In this lesson we will be focusing on scientific notation, and our essential question for today is, how can we use powers of 10 to write very large or very small numbers in scientific notation? So first of all, let's start out with why we need scientific notation. We need scientific notation to write very large and very small numbers. These numbers are a major part of our society. For example, there are many large numbers in our society, such as the number of cells the human body has, the distance to the sun, and even how fast the speed of light is a very large number, especially if you look at how much it is per day. We also have very small numbers in our society. Human hair grows at a very small rate. The mass of a hydrogen atom is very tiny. And TV signals travel a very far distance in a very small amount of time. When publishing facts like these, we need a more compact way to write these large and small numbers. That way we don't have to constantly write out 0.00000000 or 1,200,000,000. It alleviates writing those zeros that hold place value. The solution to needing a more compact, meaning a smaller way of writing it, is scientific notation. And here is the definition for scientific notation. It is a way to write very large and very small numbers using powers of 10. And if you think about powers of 10, you should be thinking about our number system. If you think about a decimal place, this is the ones column, this is the tens column, this is the hundreds column, this is the thousands column, and so on. Each place value is 10 times more than the last. 1 times 10 is 10, 10 times 10 is 100, 100 times 10 is 1,000. So every place value is 10 times bigger than the last when you go to the left of the decimal. When you go to the right of the decimal, you have the tenths column, which is 10 times smaller than the ones column, and it progresses 10 times smaller with each place value that you go. So you're going to see that place value is a big part of scientific notation because our number system, the way we typically write numbers in standard form, is based solely on powers of 10. So let's think about what we already know about powers of 10. We've learned in Unit 1 that any base to the 0 power is 1. We also know that 10 to the first power is 10. 10 to the second power means 10 times 10, which is 100. And 10 cubed means 10 times 10 times 10, which is 1,000. In Unit 1, we also learned that negative exponents can be moved to the denominator to become positive exponents. So 10 to the negative 1 is really 1 over 10 to the first, or 1/10. 10 to the negative 2 is the same as 1 over 10 squared, or 1 over 10 times 10, which is 1 over 100, 1/100th. 10 to the negative 3 similarly is 1 over 10 cubed, which is 1 over 10 times 10 times 10, which is 1 over 1,000. Now, why I show you this is to help you separate a key piece to powers of 10. Let's consider 10 to the 0 the middle. Let's let the number 1 be the middle. If you look at the powers greater than 10 to the 0, all the positive exponents, the result is always going to be a number more than 1. And if you look at the negative exponents, the number will always be less than 1. See how they are all fractions? So what you can conclude from this is, if you see a negative exponent in the numerator, you will know that it is a small amount. And if you see a positive exponent in the numerator, you will know that it is a large amount. This is the basis of scientific notation, but we'll talk about how to use it here in a minute. Scientific notation has a specific format. It always looks like a number times a power of 10. So in other words, you have some number multiplied by 10 to a power, an exponent. Now there are some stipulations on what the format can look like. The number here at the beginning of scientific notation must always have only one digit to the left of the decimal and no ending zeros. So for example, the number 5 could be written here because that's 5 point, that's a whole number, and that leaves us with one digit to the left. 3.2 could be written there because it has one number, one digit to the left of the decimal. 8.15089, that is a number that could be written here because if you look at the decimal, there is only one number to the left of it. What I mean by no ending zeros is you wouldn't write 5.0. Your last numbers in your decimal should not be zeros. Now, times 10 is always part of the format of scientific notation. So every scientific notation that you will ever write will always have times 10 because that's what scientific notation uses, powers of 10. Now, a key part to scientific notation is the exponent. The exponent indicates how big or small of a number the amount is. If you see a negative exponent, then it will equal a small number. If you see a positive exponent, it means it's a large number. Notice, a negative exponent does not mean a negative amount. A negative exponent means a small amount. A positive exponent does not mean a positive number. A positive exponent means that it is a large number, more than one. So we have 3 goals for today's lesson. Our first goal is to be able to convert standard notation to scientific notation. So start with the way we normally write numbers and write them in scientific notation instead. Our second goal is to do the opposite. If we are given scientific notation, then write it in standard notation. And our third goal is to use scientific notation to represent or solve real-world problems. So let's start with our first goal. Our goal is to convert standard notation to scientific notation. We want to be able to do this for both large and small numbers. So let's start with our first large number. Remember, the format of our scientific notation will always say a number times 10 to a power. Now, think about the number we're allowed to write here. Is it allowed to have zeros at the end? No. So it can't have any zeros at the end. We also need only one number to the left of the decimal. So if I put the number here, if I put the decimal here, I wouldn't have any numbers to the left. If I put it here, I will have one number to the left of the decimal. So I should write 3.2. Now, 3.2 is not the same by itself as 3,200,000. So we need to describe the place value difference between where we put the new decimal and where the old one was. Well, where was the old decimal? Here at the back. Now remember, each place value in a number is a power of 10. So here is one place value, so that's 1 power of 10. Here's a second place value, so that's 2 powers of 10, 3 powers of 10, 4 powers of 10, 5 powers of 10, 6 powers of 10. So I'm going to write a 6 as my exponent because the difference between the new and the old decimal was 6 place values. Notice I cannot count the zeros. There are only 5 zeros. I must count the place values difference between the new and the old decimal. Now, the last thing to do is look at this exponent. This is a large number, so it should have a positive exponent, and this is a positive 6, so we're finished. Our scientific notation is 3.2 times 10 to the 6th power. Let's look at another large number example. Now, if you look at our number, we know that it's in standard notation, so we're going to write it in scientific. A number times 10 to a power. Think about this number. I can only have one number to the left of the decimal. So my new decimal is going to have to go right here because then there's only a 7 to the left of the decimal. So I cannot write any zeros. So I'm just going to write what's left, 7.235 times 10. Now I need to figure out the place value difference between my new and my old decimal. So I will see how many place values difference there are. 1 place value, 2 place values, 3 place values, 4 place values, 5 place values, 6 place values, 7 place values, 8 place values, 9 place values, 10 place values. So I'll write a 10 as my exponent. It is a positive 10 because this is a large number. So my scientific notation is 7.235 times 10 to the 10th power. Now let's look at some small number examples. This is a very small amount. We know it's small because it has leading zeros. And if you look, there are no numbers to the left of the decimal. So that means this is less than 1. As part of our scientific notation, we need to have a decimal times 10 to a power. The decimal can only have one non-zero number to the left. So if you cross out all the zeros, all that's left is the 4. So I'm going to have to put my decimal here so that there's one number to the left. So all I need to write on my line is the number 4 because this is a whole number. So I have 4 times 10 to a power. Now the power is going to be the difference between the old, right here, and the new decimal. So here's 1, 2, 3, 4, 5, 6, 7, 8 place values. So I'll write an exponent of 8. And since this is a small number, it will be to the negative 8 power. So scientific notation, this is 4 times 10 to the 8th power. Let's look at one more small number in standard and convert it to scientific notation. So here we have a small number. We know it's small because there are no wholes. This is less than 1. For scientific notation, we need a number times 10 to a power. The number can only have one digit to the left of the decimal. So I'm going to have to put my new decimal here and write 1.25. See how there's only one number to the left. For my exponent, I'm going to find the difference between the old and the new decimal. So here's 1 place value, 2 place values, 3 place values, 4 place values, 5 place values. And since this is a small amount, we need a negative exponent. So this is the same as 1.25 times 10 to the negative 5 power.